There is an archive working paper. I've had trouble getting the most recent version up. There's a very nice LaTeX version, which I'm hoping will be up very shortly, but it's not terribly different from the not as nicely formatted Word version that's up there now. So I'm going to sweep a few technical details under the rug, and if you want to understand those, they're in the working paper, which has the same title. So some folks in this room are experts on missing imputation. One person even invented the idea. But I'm going to give a brief motivational example on why imputation matters, because I meet people at conferences who sometimes say, well, I've used imputation. It's kind of a pain. It never makes a difference. But it really makes a difference in some situations. This is new research that I'm kind of excited about. This has to do with education reform in Chile. So the Chilean government attached high stakes to its tests in 2008, its nationally required tests, and an immediate response starting the year after high stakes were attached were that the number of students who missed these high stakes tests doubled from about 8% to about 15%. And it wasn't just any students, it was students who tended to have low grade point averages and probably would have done poorly on the test. So by imputing the missing test scores, we were able to show what average test score each school would have had all the students taken the test, and what the average test score the school actually reported. And this ends up being very important because the Chilean government classifies schools as inadequate, intermediate, or advanced based on their average test scores. And you can see from this scatter plot here, these are the scores that the schools would have reported if everyone had taken the test, including our imputed scores. These are the scores that the schools actually reported. And you can see that the scores the schools actually reported are typically above this line of equality here. So schools are overrating themselves in their reports to the government. And about a significant fraction of schools that would be classified as inadequate if everybody took the test are instead being classified as intermediate. And that percentage has approximately doubled since these high stakes tests went in. So this is a good research application of multiple imputation, and it's also, there's a possible policy angle here in that when we were considering ways to solve the problem, policies that might solve the problem, we thought, what if the Ministry of Education just imputes missing test scores? Then that will basically destroy any incentive schools have to have students miss the tests, and schools may feel more comfortable, in fact, making sure that students take the test than taking their chances on the Ministry of Education's imputation model. So I see this as having an important application. Also, it turns out the one impressive thing about these high-stakes tests is that they had a bigger effect on low-income children than they did on higher-income children. They raised low-income children's scores more, but it turns out the effect on low-income students was overestimated by about 40% because of missing test scores. So it's a pretty startling example of how important missing values are and how multiple imputation can be an important solution. So with that motivating example out of the way, let's proceed to getting some notation in place to introduce some concepts, some of which are familiar and some of which are new. If we had complete data, we'd use the expression y sub com for that. But in fact, we have incomplete data in the situation we're thinking about, where we have some missing values indicated by y sub miss and some observed values indicated by y sub obs. We have a parameter vector, theta, which governs the distribution, possibly of the complete data, or at least of the missing values given the observed values. And we're going to assume that values are missing at random. We can loosen some of these assumptions, but for present purposes, we'll assume they're missing at random. We can apply maximum likelihood to either complete or incomplete data. If you apply it to complete data, you get this estimate here, theta sub com. And if you apply it to incomplete data, you get what's called the full information maximum likelihood estimate, theta sub ml. And you can do that using the EM algorithm invented by Dempster, Laird, and Rubin. And either one of these approaches will give you consistent estimates, but of course, if you have complete data, you're going to get a smaller variance of your estimate than if you have incomplete data. So we use v sub com to indicate the variance of the complete data estimate, and v sub ml to indicate the variance of the observed data maximum likelihood estimate. And you can invert either of these variances to get the information. So there's more information, there's greater information in the complete data than there is in the observed data. So there are a few quantities that get defined here. So the observed information is the inverse of the observed data estimate. The complete information is the inverse of the variance of the estimate that we would get if we had complete data, and the difference between those is the so-called missing information. And you can define a fraction of missing information by saying it's the information we have in the observed data over the information that we would have if the data were complete. And there's also a fraction of missing information, which is the complement of the fraction of observed information. So there's not a whole lot of notation in this talk, but I get it out of the way in the first couple of slides. We do need this. Oh no, there's more notation. Okay, so in addition to these maximum likelihood estimates, you can obtain what can be called a posterior draw estimate, and that's an estimate that's drawn at random from the posterior distribution of the parameters given the missing values. Typically what you do is, in practice what this works out to be is that you basically draw this posterior draw estimate from a distribution that's centered near the maximum observed data maximum likelihood estimate and has a variance that's approximately equal to the variance of the maximum likelihood estimate. And these posterior draws can be obtained through Markov chain Monte Carlo, and Honecker and King have shown that they can also be obtained using a bootstrap procedure. These give you, the posterior draw estimates are consistent, like the maximum likelihood estimates, but they have about twice the variance. And so they're, in a sense, they're less efficient, but they also, this variance has a purpose. It helps you to propagate uncertainty through the processes that follow obtaining the estimate, and that ends up being very important in multiple imputation. Okay, so let's talk about what multiple imputation is. It was invented more than 30 years ago by Don Rubin, who's sitting here.
Can I just ask a clarification question?
Sure.
ML, you just mean the ML estimate from the complete cases?
No, it's not from the complete cases. It's from the complete and the incomplete cases. Okay. It's conditional on the observed values. Okay. So you typically have to make some assumption about the distribution, but the simplest assumption you could make might be that you have a multivariate normal distribution, in which case, in a case with some missing values, the remaining values are also multivariate normally distributed, and so they contribute to the parameter estimates as well.
So both your estimators are actually achievable. It's not that you have an oracle estimator.
Well, the oracle estimator is the complete data maximum likelihood estimator. That's the estimate that you would get if you had complete data. But the
observed data thing is the one you
the observed data maximum likelihood estimator, also known as full information maximum likelihood estimator, is something that you can actually achieve, and it's implemented in a variety of software, especially the structural equation software is really good with this. So M+ has it, AMOS has it, and it can be very convenient in some software. Multiple imputation was invented 30 plus years ago. It's been widely available in software for in the neighborhood of 20 years. And the newer software is increasingly flexible. Some of it's developed here. The Amelia package is an example. It used to be in the early days of the software, you had to assume that everything was multivariate normal. But now there are more flexible packages that allow you to account for the fact that your data may have a nested structure, it may be longitudinal. You might have variables that are not normal. And as a result of the propagation of increasingly flexible software, the method's becoming increasingly popular, although it's far from universal. And we'll talk about some of the barriers to adoption a little bit later. So basically, multiple imputation works in 4 steps. The first step is to make, there are different, actually, ways of implementing multiple imputation. This is the repeated imputation algorithm. In the first step, you make 4 copies of the data set. I call it replication. In the second stage, you impute each data set separately. In the third stage, you analyze each imputed data set separately. So all the holes are filled in now, and you can analyze each of the imputed data sets as though they were complete. And then in the end, you take the estimates from those separately imputed data sets and recombine them in a way that accounts for the variation both within and between the imputed data sets. So let's talk in a little more detail about the imputation step. You have a certain number of iterations, M iterations, capital M iterations, and in each iteration you get an observed data estimate from your observed values. And conditionally on the observed values and that observed data estimate, you fill in some missing values. So here I show you randomly imputing missing values. You obtain these imputations that are drawn from a distribution that's based on the observed values and the observed data estimate that was obtained in stage 1. Now, there are a couple different options for this observed data estimate. You can use a posterior draw estimate, and this is really what everybody does. And it's what everybody has done. It's what Rubin proposed in 1987, and it's what's implemented in all the software, and it's what everybody's done for the last 20 years. An alternative, which has barely any literature on it, is to use a maximum likelihood estimate in that first step. So you get an observed data maximum likelihood estimate, you plug that in for your observed data estimate in stage 1, and you impute missing values conditionally on it. And that's what I'm going to talk about today. If you use a maximum likelihood estimate in that first stage, you get what I call maximum likelihood multiple imputation. Whereas if you do what's commonly done, use a posterior draw estimate in that first stage, you get what I call posterior draw multiple imputation, which is what everybody means when they say multiple imputation. But I have to make this distinction here because there are two flavors under consideration. So there are some advantages to maximum likelihood imputation. The clearest advantage is computational efficiency. So, whoops, not this one. Yeah, if you use posterior draw multiple imputation, then you have to take a new posterior draw in each iteration of the imputation cycle. And that typically requires a procedure like Markov chain Monte Carlo, or you can do it with the bootstrap, but you need a new estimate in each iteration. Whereas if you use maximum likelihood multiple imputation, then the estimate that you have in this first stage here is the observed data maximum likelihood estimate. It's unique. You only need to get it once, and then you don't need to revisit step 1. You can just iterate step 2. So there's some computational efficiency in not having to iterate step 1 of the algorithm. And there's some additional computational efficiency in that it's actually easier typically to get the maximum likelihood estimate than it is to get the posterior draw estimate. So the maximum likelihood estimate can be obtained by the expectation maximization algorithm or other methods in some situations. And it typically requires less coding. You have fewer settings that you need to provide the user with. For example, you don't need to come up with a prior. There are fewer diagnostics. There are fewer errors. And there are fewer errors presented to the user than if you use Markov chain Monte Carlo, for example.
But
Yes.
the uncertainty in the point estimate isn't in there. So you mean?
Pardon?
But the uncertainty in the point estimate is not represented.
We'll get to that.
Uh,
Okay. So, right. So it's going to be computationally easier. Now, computation is important. If you have a method that's faster and easier to implement, it's going to accelerate innovation. So if you want to adopt the method to work with a different data structure or work with a different distribution, it's going to be easier to get that up and running. And this is important, I think, because a barrier to adoption of multiple imputation is that people often perceive it as being slow and difficult to work with. And so anything that can accelerate the process, I think, would be helpful for the adoption of the technique. It also will be possible with a faster flavor of multiple imputation to improve the scalability of the method. And scalability, yes, please.
So I'm trying to parse out how much of this you're getting because of also the assumptions that you're building into the maximum likelihood routine about multivariate normal, et cetera.
Oh, well, the assumptions are a different matter. I mean, they're often, I'm assuming the same assumptions, you can use the same assumptions for both approaches. So,
Sure, but some of the sort of more posterior draw sort of thing, presumably you would have a little bit more flexibility because you have a choice over some of the priors, et cetera, that you're using.
Yeah. You can build a prior into this maximum likelihood of multiple imputation as well. And in fact, it doesn't need to be a maximum likelihood estimate. It can be any estimate in the first stage that's asymptotically efficient. And yeah, you can make any distributional assumptions you want. I think it could be adapted to work with non-parametric technique like the hot deck, but we'll get to all that. Scalability is, so I can see you want to get into the meat of the matter, but I'm still going to the motivational stuff. Scalability is really important because data has gotten a lot bigger, famously bigger. When 10 plus years ago, we would often refer to a large data set as having 10 or 20,000 cases, some federal survey. Now I'm pretty routinely working with data sets that have a few million cases. And when I worked at JP Morgan Chase, we processed 500 million debit card transactions a month. So a technique that is perceived as slow is going to be hard to adapt at somebody who works with at a firm that works with big data. Models are often also updated more frequently. So 10 plus years ago, in a business context, you might update a model every year, every 6 months. Now there are some applications that update models continuously. And in addition, the number of imputations that's recommended has gone up. So in the early days of multiple imputation, really up until about 10 years ago, it was pretty common to recommend using just 3 to 10 imputations. Now there's some literature suggesting that under some circumstances you want to use as many as 200 or 300 imputations. And that's a situation, if you've got a large data set, if you've got a model that's slow to fit, a situation where getting through those iterations to produce 300 imputed data sets faster could be a real asset and spur adoption, scalability.
In these contexts, is it the imputing that takes the time, or is it the fitting the model over and over?
It can be either. It varies from situation to situation. I often find myself in a situation where the imputation is slow and the model is slow. But there can be situations where the model is fast and the imputation is slow, or vice versa. Okay, so in addition to this computational efficiency difference, there's also a difference in statistical efficiency. So you're going to get more efficient multiple imputation estimates if you use a more efficient observed data estimate in stage 1. So, and that's, I stated before that the posterior draw estimate is going to have about twice the asymptotic variance of the maximum likelihood estimate. And that's going to propagate forward into the efficiency of the multiple imputation estimates.
Sorry,
So-
twice. Sorry, can you go back?
Mm-hmm.
So it's twice the variance. Well, yeah, but it's the wrong. It's the wrong. And maximum likelihood variance is wrong. Right?
Is it? I mean, you can use a maximum, you can apply observed data maximum likelihood estimation to a missing data problem and get a variance that's correct in the sense that it reflects the sampling variance.
Reflect the uncertainty in the point estimate. Right. I mean, maybe I didn't understand what that estimator is, but I thought what you were doing is is you're just conditioning on the point estimate and not using the fact that there's a variance of it. The point estimate of the first stage parameter. Is that right?
So we're going to talk about variance estimation in a couple of slides. Maybe that'll address your question. But you can, so when you apply full information maximum likelihood estimate, you get a point estimate out, and you can get an estimate using some techniques. You can get an estimate of the variance as well, which is valid over resampling.
So you want to just get the point estimate out and just use that point estimate?
For this application, all you need is the point estimate. For other applications,
You're not going to fill in the data and do the multiple imputation thing.
oh no, no. We are going to do that. So you get the maximum likelihood estimate in stage 1, and then you fill in the imputations conditionally on that maximum likelihood estimate in stage 2.
But if you fill it in conditional on the maximum likelihood point estimate,
Mm-hmm.
then aren't you missing a source of variability? Right? It's like I mean, in a regression,
Mm-hmm.
if you want to make imputations of y,
Right.
then you take a random drawer of beta from its posterior distribution, you multiply by x, and you add a random drawer of epsilon. It feels like you're skipping that first stage.
You're talking about using regression for prediction.
Just the simplest possible version of what you're doing.
Mm-hmm.
Right. So if I understand what you're doing, you're getting a point estimate for beta.
And a point estimate for the residual variance.
Yeah.
Mm-hmm.
But you basically take a random drawer of epsilon, and you're adding it to x times beta hat.
Right.
And you're not drawing beta hat from anything.
That's right. That's the difference between these two approaches. In the posterior draw approach, then you would be drawing beta hat from its own distribution.
Wouldn't the variance of y be too small because you're missing the source you're missing estimation variability. You're assuming you know the point estimates exactly. If you have an enormous sample, then okay, but I mean, I'm not saying it's necessarily going to yield really bad estimates, but we should recognize that the uncertainty is going to be wrong and the imputations may be wrong. it tends to work out very well in practice, but,
Well, wrong for what purpose?
well, that's the question, right?
Yeah. So the purpose that I'm focused on here is using multiple imputation to get a point estimate and a valid variance estimate, which is a common purpose for multiple imputation. It's not used to predict individual
Point estimate
cases.
of from a second stage analysis.
That's right.
basically.
That's right.
Right.
Yeah.
So to do that, I think you would want the uncertainty from the point estimate in there.
Mhm.
That's not at
Yeah.
the moment.
This is definitely, this is the Bayesian philosophy behind posterior draw multiple imputation. It's perfectly valid. I'm going to talk about this alternative approach, maximum likelihood estimate, and we'll see how well it can work.
And you're claiming that the frequentist coverage of confidence intervals made out of your method, you'll get correct coverage.
Yeah, you need to use different formulas to get the confidence intervals, but if you use appropriate formulas, you can get correct coverage. Yeah.
Yeah, you can't use the standard combining rules.
That's,
Right.
that's the fixed kind.
which
Right.
you-
Right.
you
So
just add up with an in between
Yeah.
because the between is too small.
exactly.
So-
Yeah.
so
Right.
I presumably you can talk about how you correct that.
Exactly.
And have different combining rules.
So basically,
But then the
you're saying
variance is
you-
immaterial.
So you're basically saying that if your ultimate purpose to estimate thetas, you don't need to draw the posteriors. But if you have other purposes, say estimate the variance of y or some kind of variability in the data set, then
Well,
this-
the variance of y could be part of theta, right? It's a parameter.
yeah, but you would be underestimating the whole variability of the variability of the whole data set, right?
You don't actually underestimate the variance of y. We'll get to this. So our goal, let's say, okay. So right, I can see I've been perhaps unnecessarily provocative. So here's how you get a multiple imputation point estimate, right? So you make several copies of the data set. In each copy, you analyze it as though it was complete, and you get some estimates. I'll call those single imputation estimates, abbreviated SI. So now you have MSI estimates, and you average them to get a multiple imputation estimate, a point estimate, MI. And there are two flavors of MI. The traditional flavor is what I'm calling posterior draw, multiple imputation, PDMI, and the new flavor that I'm talking about is maximum likelihood multiple imputation, MLMI. So the maximum likelihood multiple imputation estimate will be more efficient. It'll have a smaller variance. Here are some expressions for the asymptotic variance of both of these estimators. So the posterior draw multiple imputation estimate will have a variance that's equal to the variance of the maximum likelihood estimate plus 1 over m times that same variance times the fraction of missing information. Whereas the maximum likelihood multiple imputation variance will be equal to the variance of the maximum likelihood estimate times 1 over m times the complete data variance, the variance that you would get if you had complete data, times the fraction of missing information. Because this complete data variance is smaller than this maximum likelihood than this observed data variance, the variance of the maximum likelihood multiple imputation estimate is going to be smaller than the variance of the posterior draw multiple imputation estimator. So it's a more efficient point estimate. The big question is, can we construct appropriate confidence intervals around it? So this has some implications for the number of imputations you need. If you want to get 95% asymptotic relative efficiency, so as you increase your number of imputations, your estimates get more efficient, but they can't get more efficient than the efficiency of the observed data maximum likelihood estimate. So if you use that as a kind of asymptotic limit, then you find that under posterior draw multiple imputation, if you want 95% asymptotic relative efficiency, then your number of imputations has to be about 20 times your fraction of missing information.
So they have lower variance. You haven't shown that they're, in some sense unbiased or consistent or something like that. So we don't know that they're more efficient.
No,
Lower variance.
they're consistent, they're unbiased. Well, they're asymptotically unbiased, they're consistent,
Well,
and they have lower variance.
It depends what the quantity of interest is in the second stage analysis,
Mhm.
right? If it's the probability that y is greater than 4,
I see.
something like that,
Right.
then it would be biased.
I don't know. I mean, so I'm focusing here on the quantity being theta that we're interested in. Yeah, if there's some,
If
if there's some,
quantity's theta, well, sorry, what's theta?
theta is the parameter that governs the distribution of the data.
Okay, then there's no second stage.
Well, there is a second stage.
But you don't need a second stage if you already fact, you don't even need to impute the missing data.
Mm-hmm. So, okay, so this is a different conversation, is in what situations do you want to impute missing data, and in what situations are you content with the maximum likelihood estimate from the first
Yeah,
stage?
so that's
Yeah.
where we're talking past each other. So
Right.
I totally agree that you have a good estimate of theta.
Mm-hmm.
But then if you want to calculate a different quantity by taking the missing data and filling in the missing data matrix and then running some other kind of procedure,
Mm-hmm.
then some quantities can be calculated from that setup. You know, the mean probably could be, my guess is. But some quantities, you would get a biased estimate, I think.
That's right.
Unless you added another stage of variability, like you
Mm-hmm.
could do the bootstrapping thing, or you could draw theta hat from its posterior, or
Right.
there's a number of other approaches.
So for a situation like the Chilean situation, where we're trying to estimate the number of schools that are in the wrong accountability category, there might be an underestimate of that using this procedure.
I
You're
mean,
saying, yeah.
It depends.
Yeah.
It could certainly be biased. You know, it depends.
Yeah.
I mean, there certainly is a quantity of interest from that data set after you've imputed it that you'll get the wrong answer, and it could be arbitrarily far off. What happens in practice? You know, a lot of times stuff comes out in the wash, but certainly it's a biased estimator, so it's not efficient. It's just as lower variance,
So-
except for theta.
So I think this is an interesting kind of follow-on topic to talk about. What I'm focused on here is the common situation where social scientist wants to estimate some regression parameters, for example, present them in a table with appropriate standard errors. So, which is a very common use of multiple
Say
imputation.
if your outcome is like income, you want to estimate income inequality.
Mm-hmm.
Would
Right.
that be underestimated?
No, I don't think so.
That would
Something
be
like the Gini coefficient, you get the wrong answer.
yeah, you would get the wrong answer. Right.
It's nonlinear transfer, like, yeah, nonlinear transfer.
Yeah, I mean, all this stuff works asymptotically, and so if everything is linear and the posterior distribution of likelihood functions are all normal, which they rarely are, then all this works.
Because, I mean, in that case, if you're just running regressions, then it's just a beta coefficient is just a simple transformation on the theta matrix anyway. So it's not going to be, you're going to get, everything's going to be fine. But I think in the more common, yeah, I think just the more common, I don't know, more common, where you just impute, and that's like a first stage to messiness in the second stage. It's, I mean, I just want,
yeah.
seeing the variance estimation will be
Right.
helpful, I think.
Yes, yes. So the messiness in the second stage could be very interesting. But let's talk about a second stage that's,
Can you just quickly go back one
Yep.
slide?
Yeah. Or maybe this one.
Where you define what your theta hat is?
Yeah, right. This one.
So is theta hat obs and theta hat SI, are these the same parameters or are they different?
Well, the parameter is theta, right? So that's the same
That's
throughout,
what I
yeah.
mean. So-
But there's an observed data estimate that you get from the observed values alone.
I see, so you really are, you are re-estimating your theta with your complete data.
That's right,
It's
yeah.
the same theta that you use to impute your missing data.
Well, the theta is the same, but the estimate is different.
Right, but so you basically estimate theta, you use that estimate of theta to impute your data, you re-estimate theta.
And then come through and estimate theta again. Now, you could estimate a different quantity in the second stage, which I think is one of the most interesting applications. But this is done very commonly.
Okay. Well, there's no, I mean, just to, so if you're interested in theta, then don't impute. You already have, you have a great estimate of theta. If you're interested in estimating some other quantity, then you go to the second stage. And I think for certain quantities, you'd be highly constrained, but for certain quantities, you'd be fine. But for other quantities, you'd probably want to add one level of variability. So I think you don't have that here, but I don't think it would be difficult to add. And my guess is everything that you say from now on could continue, and it would be the same, except you'd have another level of draws that you could just add to this. So,
Mhm.
so we can just ignore that for the moment.
Okay, let's have a look here. Okay, so let's proceed to variance estimation. So we have two possible multiple imputation estimates we could get. There's the traditional posterior draw multiple imputation estimate, a point estimate, and that'll have a variance that's associated with it. And there's the maximum likelihood multiple imputation estimate, point estimate, and that'll have a variance that's associated with it. And there are different ways to estimate the variances of these multiple imputation estimates. There are three approaches. One is using the within-between formulas, one of which is the formula just about everybody uses that was invented by Rubin in the 80s. Another is to use the bootstrap. And a third approach is to use a score-based, is to use the score from likelihood theory. So let's talk about the WB formulas. So the W and B refer to within and between variance components. So we've already talked about how you get a point estimate. You analyze each of these singly imputed data sets as though it were complete. You average the point estimates to get a multiple imputation point estimate. Each of these when you analyze these singly imputed data sets as though they were complete, you also get from those analyses an estimate of the standard error. And that estimate is consistent for what the standard error would truly be if the data were complete. If you take those, if you square those standard errors and average them, you get an estimate of the within variance. And then there's also the between variance, which is if you look at the variance of these singly imputed point estimates across data sets, that estimates the between variance. So these are widely used variance components in multiple imputation, and they're used for, they're used for this formula. Whoops. Sorry. So here's an example. So let's say we have 4 imputed data sets, and from each of those we get an estimate of a quantity, which in this case is around 958. It's going to vary a little bit from each data set, from one data set to another. The variance across those data sets in this case is 4. That's the between variance. And there's also a standard error estimated from each of the 4 imputed data sets, which is, in this case, is 3.3. If you square that and average the squares, you get a within variance of 11. There's an issue with this between variance, which is that it's estimated from a sample size. It's a variance estimated from a sample size of m. And if m is small, this variance is going to be somewhat unreliable, and that you would get a significantly different or substantially different estimate of b if you imputed the data again. And that's not a problem if the fraction of missing information is small, but if the fraction of missing information is large, then this b, this between component, looms pretty large in a lot of the calculations that are done, and it can give you estimates of the variance that are relatively unreliable in the sense that you might get noticeably different estimates of the standard errors and confidence intervals if you reran the analysis. And for that reason, that's the reason why larger numbers of imputation are recommended now than were recommended, say, 10 or more years ago. So here is the WB formula that everybody knows. It was invented by Rubin in the 1980s, and it involves taking the within variance, adding the between variance, and then adding 1 over m times the between variance again. And it gives you a consistent and, in fact, unbiased estimate of the variance of a posterior draw multiple imputation estimate. This b component here can be somewhat unreliable and noisy, and if it's a large part of this variance estimate, as it can be when the fraction of missing information is large, it can make this variance estimate fairly noisy, and to reduce that noise, there are some papers that have been published over the last 10 years recommending using as many as 200 or 300 imputations. And that's not always practical if your second stage analysis runs slowly if you have a large data set. So that formula doesn't work under maximum likelihood multiple imputation, but there is an alternative formula that does work, and it uses the same components, and here it is. You take the within variance, you multiply it by an inverse of the estimate of the fraction of observed information, and you add 1 over m times the between variance. So this fraction of observed information is estimated by subtracting a fraction of the missing information from the identity matrix, and this fraction of missing information is the quotient of the between information and the between variance and the within variance. So this is another way of combining the within and between variances that gives you a variance estimate that's actually consistent for maximum likelihood multiple imputation. This is a new formula. Consistency, the formula is consistent, but consistency isn't everything. This formula has a practical problem, which again hinges on the variability in this in the estimate of the between variance here. If you have a large fraction of information and a small number of imputations, then this between variance can actually, in some cases, be larger than the within variance, just because of sampling variation, and that'll give you a fraction of missing information that's greater than 1, and that results in a negative fraction of observed information, and therefore the whole variance estimate can be negative. So we don't want that. And in order to avoid that, I apply a shrinkage function to the fraction of missing information. The shrinkage function involves some gamma functions, and it's in the archive working paper. And when you apply shrinkage, you get less variable variance estimates, as well as estimates that are guaranteed to be variance estimates that are guaranteed to be positive, fractions of missing information that are guaranteed to be between 0 and 1. The price of shrinkage is that you get a slight downward bias. But none of this is a big deal if unless the fraction of missing information is large. So I'll do some simulations where it turns out the fraction of missing information is less than 50% or so, which covers most practical situations. The bias in these shrinkage estimators is not a big deal, and you end up with about the right coverage.
Can you say a little bit more about how you're doing the shrinkage?
Yeah, so we know that basically I take the posterior distribution of the fraction of missing information, and I truncate it at 0. Truncate it at 1, and then I take the mean of the truncated posterior. There are other shrinkage functions that could work it well as well. It gets a little bit detailed, but it's in the appendix of the archive working paper. It's a Bayesian procedure.
For a general ballpark idea,
Sure.
like in your Chilean case, if 20% of the students skip the reading test and 20% skip the math test,
Mm-hmm.
and whatever, 10% of them, half of those skip both. I mean, does that turn out to be a small, manageable amount of missing information? Or I don't really have any sense of what
Oh,
the fraction of
yeah. The missing information it's not the fraction of values that
I
are
understand
missing.
that. That's
Yeah.
why I'm asking that.
Yeah, typically it'll be smaller than the fraction of values that are missing, because there's some the more predictable those missing values are, the smaller your fraction of missing information is. So in the Chilean case, for example, we had the students' grades, we had their attendance, we had their income. That explained about 40% of the variance in the missing test scores. And so our fraction of missing information, even though we had 15% missing values, our fraction of missing information was only about 5%.
So sorry, I'm
Sure.
hung up on this. So you have to do this in the case where the between is greater than the within.
You have to shrink in the case where the between is greater than the within?
Is that what I thought?
Yeah, so yeah, shrinking is not optional in that case. You can shrink all the time, and it actually
Well,
gets
that's
you,
what I'm
yeah.
saying. Like it seems like, in some senses, that's like an odd sort of thresholding type thing to do. Like all of a sudden you hit, you go epsilon over between greater than within, and now all of a sudden we're having to apply this. Right?
Yeah, no, I don't, I shrink all the time when I apply this, because the shrinkage function takes advantage of the fact that we know that the estimand for B is smaller than the estimand for W in this context. We note the fraction of missing information
But
is less than
shrink
1.
all the time if you know that there are downsides, and in some set of cases, that is to say bias downwards, but in some set of cases, you don't have between greater than within. So why always shrink?
Why shrink all the time? It reduces variability in the estimate, like shrinkage functions often do.
Sure.
And it has very little bias, except in the situation where the true fraction of missing information is close to 1. So you're not actually, it doesn't actually change the estimate very much when the fraction of missing information is small. And when it does change it, it's helpful in reducing variability, and there's little bias that comes with it. So it's a good trade-off.
Actually, there's a larger literature about this situation and using multiple imputation to preserve confidentiality, which is being done in U.S. Census and in various German databases as well. You're basically filling in a whole population with imputed values, the population from which the sample came, and then you're drawing new samples that you're releasing from this hypothetical population. So you release no real data, is the idea, only non-confidential data. And in that case, the combining rules are different. And in fact, they have a subtraction which is based on the same kind of method of moments ideas. And there too, you can have a problem with negative variance estimates. And there's several papers, I think, by Jerry Ryder, who's at Duke, and Rod Grunau from the Institute of University of Michigan, We did some early stuff 20 years ago on it, just some initial stuff. That's pretty crappy because it's method of moment stuff. But the newer stuff is better. And so and it does exactly what you say. Use it all the time, and you don't have a hard threshold when you bring it in.
So these within between formulas, they can require many imputations. So the point estimates that you get with multiple imputation, they converge to their toward their asymptotic limits. They get pretty close pretty fast with few imputations. But
Just make
these,
sure I'm reading this correctly. So in the Chilean example, the fraction missing information you said is less than 20%, right?
yes,
So there it doesn't make any difference.
right, right. Yeah, in many practical situations, the fraction of missing information will be relatively small. So,
Which is not true in this confidentiality context.
Yeah.
Because the fraction of information can be very large because effectively you're filling in the whole population and taking samples from that. There's a lot of information that's missing intentionally because you're releasing no observed data. That's the whole purpose of it.
interesting. There are other ways to calculate the variance of an MI estimate. One approach is the bootstrap, and this was first proposed by Efron in 1994. A difficulty in 1994 was that at the time it was believed that only 3 to 10 imputations were necessary for multiple imputation, and so the bootstrap seemed to require a lot more replications, seemed to be computationally intensive. The context has changed now that we have literature suggesting you need 200 or 300 imputations for some situations where you have a high fraction of missing information. And even if you need 50 imputations for some situations to get the variance estimates to stabilize, 50 imputations is comparable to the number of replications that you use for the bootstrap, so the bootstrap becomes a viable option. So here's a way to do variance estimation using the bootstrap. So you take a certain number of bootstrap samples, let's say 40 or 50, right? That's a kind of a lower threshold for how many bootstrap samples you would take of the incomplete data, and then you impute each of those bootstrap samples m times. And so you'll obtain b times m individual point estimates. So you've got a set of data sets that have been bootstrapped and then imputed. And if you've got, let's say, 50 bootstraps and 50 bootstrap replicates, each one of which has been imputed twice, you'll have 100 data sets, each one of which has its own estimate of theta.
And what do you do with the bootstrap sample for which the maximum likelihood estimate is not unique? Which happens with probability 1.
A bootstrap sample where the maximum likelihood estimate is not
Yeah,
unique?
because you can when you're bootstrapping, you're drawing from the missing data matrix, right?
Right.
And so with probability 1, you'll get the same value all the time, the same unit all the time, or a set of units for which
Oh,
there
right.
is no maximum likelihood estimate. And
If you have enough bootstraps resamples,
no
this
problem.
can happen.
In the limit, that's what you get.
Right,
You have
right.
Some large fraction of your samples, there is no unique estimate.
Right. Now,
And so the bootstrap is known to underestimate variability in missing data problems. Because what people typically do when they do what you're saying, they say, I took a bootstrap sample and there's no unique estimate, there's no unique maximum likelihood estimate. So I'll just discard that bootstrap sample. So I'll discard samples that lead to more variability.
yeah.
You systematically underestimate frequent sample variability.
So I've not run into that in my simulations. So I've got samples that are as small as 100 observations with 50% missing data. I bootstrap each one 50 times, impute each one of those bootstraps twice. I've got 2,000 replications of the whole simulation, and I haven't run into a situation once where there was no maximum
They
likelihood
probably
estimate.
hadn't gotten convergence of maximum likelihood estimates is what's going on.
Well, you're doing a little shrinkage too, right?
No.
There's no Bayesian shrinkage.
I'm not doing any shrinkage in this approach. So, for example, I'm fitting a regression model. So I'm taking a bootstrap sample, and I'm getting the maximum likelihood estimates using least squares, which you can do in some situations. So if only y is missing from a regression analysis, you can get maximum likelihood estimates using least squares in the complete cases.
Oh, for
And-
example, in that Efron article, in
Yeah.
the example he uses, there is no maximum likelihood estimate. And I was a discussant of that paper.
Right, I remember.
And
Yeah.
In that, Brad said, well, I sort of noticed that too, and maybe I should have used that
Mhm.
example.
He was using a very small sample, though, wasn't he? I mean, it was the kind of thing that fit in a
Well,
little
it was-
table.
I think it was
Yeah.
20 observations where he he deleted some values.
Right.
And the way he deleted values, there is no maximum likelihood estimate, because in order to have a unique maximum likelihood estimate, you have to have at least the number of observations in this regression example that is complete observations
Mhm.
that are as you have variables.
Right.
Otherwise, you can show geometrically that you have lines that don't intersect, and therefore there is no
Right,
unique estimate.
right, yes. So all my simulations are in that part of the space. In simulations, I've got 2 variables, I've got 100 cases or 500 cases. So I'm not looking at really microscopic data sets.
But still, with probability 1, you can have draws, bootstrap samples, for which there won't be a maximum likelihood estimate. And so unless you really are doing a really careful watching of what the thing is or has it converged.
Yeah.
And it's probably in a simulation. I don't know anyone who does that. Maybe you did, but to see whether you're actually converging to.
Well,
unique
I'm
points.
getting my maximum likelihood estimates through a non-iterative process.
Oh,
So
so it's a monotone pattern or something?
it's a monotone pattern, yeah. So I can use least squares, and I didn't have any difficulties in this particular simulation. There might be other situations where this could run into problems, particularly in small data, or in data where the number of columns is much greater than the number of rows or comparable to it. So anyhow, if you do this, so you've got, you impute, let's say 50 you bootstrap, let's say 50 copies of the data set. You impute each of those 50 copies, say twice. Now you've got 100 copies of the data sets. You can analyze each one of those as though they're complete. And now you've got 100 individual point estimates. You can put those 100 individual point estimates, so you can average those 100 individual point estimates to obtain a point estimate of the parameters you're interested in, theta. And you can also put them in a random effects model. So this random effects model will have 2 variance components. Its average value will be theta, or consistent for theta, and it'll have 2 variance components, one that's related to the variance that comes from the bootstrap, and one that's related to the variance that comes from the imputations. You can estimate those 2 variance components, and you can combine them to get an estimate of the variance of the bootstrap multiple imputation estimate. It's equal to the bootstrap variance, plus the imputation variance over b times m. So clearly, if b is large or m is large, that second component ends up being relatively small.
Why do you need m to be greater than 1?
Why do you need to impute each data set more than once? Each bootstrap data set? Because you need to be able to estimate the second variance component, the component that's due to imputation. So there's basically 2 components of variance in all these missing data problems. There's the ordinary sampling variation, which you have in complete data problems as well. And then there's imputation variation. So the bootstrap procedure gets at that ordinary sampling variation. And then this is actually different from the procedure that Efron proposed in 1994. You've got a second stage, which involves imputation, allows you to estimate that imputation variation.
P of em is equal to sigma e squared. So the second.
Yeah, that's the variance due to imputation.
But if you only imputed once, wouldn't the variance of your point estimates have you wouldn't be able to separate your variance components, but you
That's
get
right.
the overall variance. So
No, you wouldn't be able to estimate the second variance component.
but you'd be able to estimate the second plus the bootstrap variance together, right? Because just the variance of your theta hat should be all of your uncertainty. So I don't understand. Just because you can't estimate the 2 components, you can still estimate the overall total variance.
Mhm.
Or I'm missing something there.
I'll have to think about this, whether this could work with 1 imputation. Currently, I'm doing with 2. Right. So, yeah, it's funny. Most people think that when I present this, most people think you must need more imputations per bootstrap. I've never heard anybody say you need less. It's an interesting suggestion. There's a third way to estimate the variance of a multiple imputation point estimate. It's a score-based formula. And let's review briefly what the score is. So score is the gradient of the log likelihood. And in complete data, the variance of the score is the information in the complete data. And the score, if you have independent identically distributed data, the score adds up across the cases. So each case contributes something to the score. And the contributions of the individual cases the variance of those is equal to the information over the sample size. So it turns out that if you estimate the score function from multiple imputed data and you estimate the contributions of the individual cases to the score, then in the cases that have some imputed values, that contribution to the score will have components of variance that lie between cases and also that lie between imputations of the same case. So again, you end up with a components of variance model. And using this components of variance model, and it turns out that you end up with two components of variance, one of which estimates the variance of the maximum likelihood estimate, one of which estimates the observed data variance, and one of which estimates, the observed data information, and one of which estimates the missing information. So you take those two components, and you can get a new estimate of the variance of a maximum of a multiple imputation estimator. It's equal to one of the variance components from the decomposition of the score function plus 1 over m times the between variance. I'm being a little bit quick here because I see that we're nearing the 1:15 mark. I want to make sure that I show you some of the simulation results that'll make this more concrete. So this approach of decomposing the variance of the score function, it actually works under either of the imputation procedures that we've talked about. In fact, the bootstrap procedure that I talked about also works under either of the imputation procedures that we've talked about.
But is this variance v hat ml WB,
Mhm.
is that consistent for the variance under ml? Like the VML, v sub ml that we saw earlier? Because then,
Yeah.
So,
It is.
because it seems like here you could, why not, I mean, as a hypothetical, why not just skip imputation completely, take your 1 point estimate that you're using as your point estimate,
In stage 1, yeah.
and just use this as this v hat ml WP as your estimate of the variance of that, and do transformations like you like to get the, you know what I mean? Why not just use that, because it's going to be more efficient?
Yeah, well, so this is a separate talk, is when do you want just the maximum likelihood, observed data maximum likelihood estimate, and when do you want to use imputation?
Okay.
But this particular estimate of the observed data, this particular estimate of v sub ml, this comes from decomposing the score function. It's different from the estimates that we've used between. In fact, I'm sorry, there's a typo here. This should be an S. It's a score-based estimate.
Right, no,
Yeah.
that I get. I get that this is different than what you were doing before, but
Yeah.
it just seems like, so the advantage of maximum likelihood is that you get to separate out the two stages of the models, and so you can have relatively simple variance calculations, straightforward variance calculations in the second stage. You don't have, it's not very complicated, but you can still use those simple calculations to get out the variance of the complete data estimator. But if you know how to calculate the variance of the parameters, the estimator, the ML estimator, it seems like, and you're going to calculate it anyway, it seems like you could just use that as the that as the variance estimate of your estimator, and just ignore not use the imputations, and it'd be more efficient, unless I'm missing something.
It sounds like you're arguing for using a maximum likelihood estimate instead of multiple imputation.
So I think a lot of what we were talking about at the beginning of the talk was that the reason why imputation exists, or the reason why it's so popular, is that you could separate out those two stages. Initially, because again, it'd be a public data repository that would do the imputation, so you couldn't. It's not feasible for the end user to do that.
Right.
Now it's more because we separate out those two stages, so we could have maybe two analysts do it, or that there's like we want to use a more complicated model in the second stage than really the imputation model is kind of generating it, and so we want to be able to separate out those two steps. But if it's going to be the case that you're going to focus on the theta hats as being the ultimate parameters of interest, or some linear transformation of them, it seems like you could just skip the imputation step and just, I think this was Gary's point earlier, and just use that v hat ml.
Right.
And if you know how to calculate it.
Yep.
I guess does that make sense?
Yeah. So there are some people that argue for that in many circumstances you actually just want to stop in that first stage. Paul Allison's argued for this, or Steve Rodenbush has argued for this, that in some stages you just want that maximum likelihood estimate from stage 1. You don't need to impute unless you want to use the data for some other purpose. Yeah. So this score-based estimation ends up being a very efficient way to estimate the variance of a multiple imputation estimator. It needs typically only 2 or 3 imputed data sets. but it's limited. You have to have independently identically distributed data. You have to be using maximum likelihood. You have to have each case's contribution to the score function. And you have to do a variance components calculation, which can take a little bit of time. One thing that,
I believe very strongly in asymptosia, which in big models is completely wrong, and the likelihood functions don't look normal at all. But they don't look multidimensional normal at all. So that's the one disadvantage to maximum likelihood and associated score calculation is you're relying very, very heavily on ellipsoidal symmetry of the likelihood function.
on the model, so you're talking about the model being correctly specified and,
Yeah.
and
Yeah, if it's-
within a
if it's
certain
correctly
family of models.
specified,
Yeah.
And the more complicated the models,
Yeah.
complicating not only in terms of latent variables models, which are very common, mixture models, they're commonly used. The likelihood functions don't look normal at all.
See, the latent variable example is really interesting because it's the latent variable software that has the most of this full information maximum likelihood stuff implemented in it.
And it's probably all wrong.
Wow.
What is it? It's just,
Well, the fact that you have something that's unobserved with missing data or latent variable model creates likelihood functions that don't have the shape that we're always assuming. And so summarizing things by a point estimate is okay, but then the standard error calculations are just axes of the ellipsoids. And if it's not ellipsoidal, they're terrible.
You're talking, this is an issue with complete data as well as incomplete data.
Well, complete data in a latent variable model, yeah.
Yeah.
But I'm sort of viewing that as a missing data problem.
Mhm.
That's the way
Because it's latent. Yeah, I see. So I want to make sure we get to the simulations because I worked really hard on those in the days before this talk. I just want to summarize these different approaches to variance estimation. So there's bootstrapped MI, which is the simplest approach. It only needs point estimates, so you don't need a variance estimate from your analysis of the imputed data sets. And it needs a moderate number of replications, maybe 50, and maybe as few as 2 or even 1 imputation for each of those. So it's the simplest approach, and I corresponded with Jamie Robbins about this a little bit, and he thought it might be robust to certain kinds of misspecification of the imputation model, which is interesting. I'll have to talk with him later about that. Then there's these within-between formulas. For these, you need not only point estimates, but standard errors from the first stage of analysis. And a disadvantage of these is that if the fraction of missing information is large, you may need many imputations, especially, and that's especially true under maximum likelihood multiple imputation. But they're appealingly simple formulas. And then there's this score-based approach to variance estimation. And for this, you need not only the point estimates, but also, and not just the standard errors, but also the contribution of each case to the score function, which is something that I've rarely encountered in practice. When you do have that situation, it's really great because you need very few imputations. You get a very efficient estimate of the variance. All right, now here's the simulations. So it's a fairly simple simulation, simulated bivariate standard normal data with a correlation of 0.5. I looked at situations where 25% of Y values were missing. I looked at situations where 50% of Y values were missing. I looked at a couple different sample sizes, 100 observations, 500 observations. I didn't look at really small sample sizes. I've done that in other work. And I looked at a couple different missing data patterns, the missing completely at random scenario, where values were deleted willy-nilly, and a missing at random scenario where Y was missing as a function of X. I did a couple of different analyses. I regressed Y on X. The more interesting situation here is regressing X on Y. The situation with missing, where the regressor has missing values is more interesting, and there are more things that can go wrong. And I conducted 2,000 replications so that I could estimate the coverage of confidence intervals to within a standard error of 0.5%. So if the simulation says that the coverage of a confidence interval is, say, 93%, then it's very likely, it's unlikely to be much above 94% or much below 91, much below 92. All right, so here are the results of the within-between formulas. So let's look first at the situation where you've got 95%, where you've got 25% missing values. And here, the maximum likelihood multiple imputation point estimates are actually more efficient, but they have wider confidence intervals. And that's because of the WB formula that's associated with maximum likelihood multiple imputation. It has fewer degrees of freedom in the variance estimate. And that was just, that's unfortunate, You do get about the right coverage rate from either of these approaches, even with as few as 5 imputations. But when the number of imputations is small, the maximum likelihood multiple imputation point estimates will have the confidence intervals will be a bit longer than the posterior draw confidence intervals. With 50 imputations, they're pretty much indistinguishable, and they both have very close to nominal coverage. And the same thing is true with values missing at random. When you go up to a situation where values are missing completely at random, well, it's actually basically the same thing. There are a couple of situations here where the maximum likelihood multiple imputation estimates, their confidence intervals have a bit lower than nominal coverage, but in most cases, you're pretty close, 94, 95, 96%. There's just a couple of 92s in this table. So the performance is all right, but it's not as good as the posterior draw multiple imputation estimates. And that's because of the way the variance is estimated. It's not because of the point estimates. When I go up to 500 imputations, I get a lot of the same issues. You do start to actually see some of the advantages of maximum likelihood multiple imputation with a large number of where it actually will give you a shorter confidence interval in some cases, although when it does that, the confidence interval tends to have a little below nominal coverage. So the WB formulas, I don't think work as well for maximum likelihood multiple imputation as they do for posterior draw multiple imputation. That's because of the shrinkage that I had to throw in and the sort of low degrees of freedom for estimating the variance. Here are the bootstrap estimates. This is with 100 cases. This is bootstrapped multiple imputation. And you get essentially identical results when you use bootstrap multiple imputations, whether you use posterior draw multiple imputation or whether you use maximum likelihood multiple imputation. So in each case here, I used 50 bootstrap replications and 2 imputations per replication. And the confidence intervals are essentially identical in length, at least to 2 decimal places. The posterior draw multiple imputations, you do see a little more variability in the length of the confidence intervals, but basically not much to choose between them. The coverage of the confidence intervals is a little bit low, in the neighborhood of 92, 93, 94%. And I got to wondering why that was, so I ran another simulation at 500 with a sample size of 500, and I found that the coverage rate of these confidence intervals came up. So I think there's a few different things that could be increased here. You could increase in the sample size, the number of bootstrap replications, number of imputations per replication, and it may be that these confidence intervals would get arbitrarily close to the nominal coverage level. Although I'm not sure. I'd have to look at some more variations in the simulation to be sure.
And the missing data pattern and all these are just the monotone. It's only two.
Yeah, there's only 2 variables. Yeah, so y is missing at random and x is complete. And then here are the score-based estimates. So here, these work really well. I've only got, let's see, it doesn't really matter very much if you use, you can see if you use 5 imputations, you get essentially the same confidence intervals as if you use 50 imputations. So a small number of imputations works really well with this approach. The confidence intervals are really short, and they are less variable than they are under other approaches in the sense that if you imputed the data again, the confidence interval, length of the confidence interval will change very little. And the coverage of these confidence intervals is typically 94 to 95%. So it works really quite well. And there are a couple of situations where you see the advantage of maximum likelihood multiple imputation in having slightly shorter confidence intervals, although it also tends to come with slightly lower coverage when that happens. So the within between estimator works a little better under posterior draw multiple imputation, and it gives you, but maximum likelihood multiple imputation gives you very similar results if your fraction of missing information isn't too large and your number of imputations isn't too small. If you use the bootstrap, you get very similar results under either PDMI or MLMI. And if you use score-based variance estimations, you also get very similar results under both PDMI and MLMI.
So,
Yes.
sorry, just wanted-
Sure.
So, kind of from a 10,000 feet perspective, and someone who hasn't done as much imputation stuff, that it seems to me that your main advantages are actually what you led off with, not with this stuff.
The
That's
computational, yeah.
computational. So
That's right.
just wrap up rock time or whatever, I don't know what you're doing this in, and show the computational time that it takes to do these things in your simulations.
Yeah, one suggestion that I've had the suggestion once before that instead of actually looking at the at the performance of confidence intervals for a given number of imputations, it might be interesting to look at them for a given amount of runtime. Yeah, the trick there is that the runtime is influenced by how long the imputations take to run and how long the analyses take to run, and that's going to vary from one situation to another. In this case, yeah, I didn't probably emphasize this enough. The MLMI ran about 100 times faster than PDMI, which could be a major advantage that allows it to get implemented in a big data context where PDMI would be impractical.
So among the three approaches,
Mhm.
seems to me that only in the bootstrap approach, you don't need to know the standard error formulas from maximum likelihood. In the other two approaches, you need to know how to calculate.
Yeah, so the bootstrap approach can live on point estimates. That's always a nice thing about the bootstrap. The WB formulas you need some kind of standard error estimate from the analyses of the individual imputed data sets. And from the score-based formulas, you need the contributions of individual cases to the scores.
Yeah, but in those cases, yeah, because you already know how to do the ML, why do you need to compute?
I'm sorry? So again, this is the question of,
It looks like only in the bootstrap approach is more advantageous in the ML because you don't need to know the ML standard error formula.
right. So yeah, there may be a situation where you have in the first stage of the analysis, you're not getting ML from a procedure that supplies you with a standard error. For example, you could have a really big sample, and you could be using a non-parametric approach that's asymptotically efficient, like the hot deck. And the bootstrapped MI approach should work in that situation. So it could have advantages in that application. Or it could have advantages in a situation where your first stage model is your imputation model is parameterized in such a way that you don't get standard error estimates out of it. Yeah. So maximum likelihood multiple imputation, it's, as you say, the advantages are chiefly computational. It does have this advantage in the efficiency of point estimates, but that doesn't necessarily translate into an advantage in the length of confidence intervals, and it's a relatively small advantage if the number of imputations is even modestly large. A real impediment to the use of maximum likelihood multiple imputation in the past has been, first of all, the limited amount of work on it. So almost all the work has been in this area of posterior draw multiple imputation, and also the fact that there was no practical way to estimate the variances. So I've proposed 3 different ways to estimate the variances. They all seem to produce variance estimates that produce confidence intervals with close to nominal coverage, and that's a big step forward, I think. It's really quite easy to implement. I've actually already implemented it in SAS, and it wasn't hard to do. All I did was I took an old macro that Paul Allison had written that implements PDMI, and it turns out there's a little setting in there that just reduced the number of data augmentation iterations to 0. So I just set that to 0, and now it does maximum likelihood multiple imputation. So if there's interest in this in the applications of this method, it would not be hard to adapt to existing software. Just comment out certain code or put a couple of options in there, and you can use existing code to implement all the wonderful models that have been implemented under PDMI. It would be very straightforward to port them over to MLMI and have both options available in a lot of software. And one reason I wanted to come here is I thought that I know that this group produces imputation software. I thought this would be a nice feature for Amelia. And then there are some extensions here, which is, although I call it maximum likelihood multiple imputation, I haven't come up with a better name for it. In fact, these same formulas work with any parameter. You can plug in any parameter estimate that's asymptotically efficient. It doesn't have to be a maximum likelihood estimate. So one possibility would be a non-parametric approach to imputation that, say, it imputes cases from the observed CDF, for example. And the hot deck imputation approach that used to be used at the census would be one approach for that. It should work, especially since census data tend to be relatively large, it should work with these variance formulas. So there's future work to be done using these approaches. And that's it, except for the references. Thanks to you. Sure thing. I got a bunch of questions during, and it's close to 1:30, but do we have time for one, or does anybody?
Now, have you thought about how this stuff would be implemented under things like mice?
Yeah.
Incompatible, potentially, I call them pigs, the potentially incompatible give samples.
So mice is where you have these alternating regression models where each variable is imputed conditionally on the others, and you have different, like you might have a linear regression for this variable and a logistic for that.
This and something else for
Yeah.
that.
Yeah, and there's a Markov chain Monte Carlo stage in that, right?
Well,
So,
it cycles around
yeah.
all of them, that's their,
Yeah.
it's Step and Burns,
right, sure,
game,
yeah.
and also it's, Raghunathan and IBE where.
Yeah, it seems to, I mean, despite the, concern about the lack of theory behind these things, they seem to work rather well in practice, and in situations, that are well understood, like multivariate normal, they produce very similar to results to what we're using. So it seems to me you could just turn off the MCMC component of that, and you'd get something like this.
I'm not sure how you would, because the way they work is, well, the simplest version is one variable is conditioned on all the other variables.
Mhm.
And then you take a random draw, and then you fill it in. Then the second variable is conditioned on all the other variables. And you don't
Right.
worry about whether these conditional distributions are compatible.
Right,
with
right.
the joint distribution. And you just do it.
But you're drawing parameter estimates at random from the posterior of each model, right?
Correct.
Yeah.
And many of these models, like our hot deck-like thing, or predictive mean matching,
Mhm.
things that for which there is no such thing as a maximum likelihood estimator.
Right.
And you can presumably make them more efficient by not drawing as much. But there's very little theory to guide you, and you certainly don't get things that look multivariate normal as effective posterior distributions. In fact, there is no focus on the parameters at all there, because the whole purpose is just it's an algorithm for generating draws. And so the diagnostics are on the draws, not on parameters.
Mm-hmm.
So it's kind of a different game.
Mm-hmm.
So it's not clear how we try to shortcut the computations. And in some way, I guess you could argue with is it really easier to do maximum likelihood when there's a coherent theory. You're supposedly drawing from one joint posterior distribution, which in reality doesn't exist. We don't have, all these models are wrong. They're all fantasies, and the only things that really exist are the values that you draw. There's famous George boxing, all models are wrong, some are useful, but
Right.
that goes back to von Neumann, actually. He was saying the same thing. So values exist, models don't. So the focus on parameters of models is sort of an aberration of statistics, not of science. So these methods, algorithms that focus on the procedure for creating draws can be very appealing. Because it's much easier to think of doing diagnostics for whether drawn values are realistic than whether parameter values, especially complicated models, are realistic.
Mm-hmm.
If you have Poisson, what's a realistic draw of a Poisson parameter?
Yeah.
It's all fantasy anyway.
Right.
But if I'm imputing counts of the number of stars in the universe for your blood pressure, that's not very good. So there's a lot of virtue, I think, in skipping, trying to minimize the focus on formal models. And you should be pulling back towards the formal model.
But I'm not sure. Just a general point. If you were, instead of doing a model or releasing a model, you were going to release in Chile to all the professors at Chilean universities just data sets of like 10 draws of their population of high school students who took both the reading and the math. Would be complete, but there'd be 10 of them. What would you be expecting them to do with that?
Well,
What would you expect them to be doing?
If they're draws from the posterior distribution, and say, well, here's how you do the combine. Analyze each one of them any way you want, and if you believe that the thing that your estimand has approximately a normal posterior distribution, then use the combining rules. If you don't think that, then you have to have more imputation, but don't use the combining rules. Then look at the percentiles of the drawn estimands.
Mm-hmm.
And because people do have intuition about what drawn values of real variables should look like, they often can have reasonable diagnostics on whether you're doing something sensible.
I haven't heard you talk about this before. So you're talking about using multiple imputation without an assumption of normality in the sampling distribution of the parameters of result. So for that, you would need a lot of imputations.
depends upon the question, yeah. Because if the estimate has a normal enough posterior distribution,
Right.
then it's okay. Otherwise, if you get away without, I mean, the concern, I'm not sure how realistic the concern with data storage or speed of computation is anymore. If a thing is easier to describe and it's easier to understand, so not as many steps in the middle to understand, you're just drawing imputed values that you think are realistic. In some ways, that's a hell of a lot easier than having to teach somebody about likelihood functions and maximum likelihood and bootstrap samples and all this other stuff that we all understand, but does somebody, a real data user, the Chilean schoolmaster, really understand that versus here's what your schools could look like? I mean, this idea of just imputing values and not worrying about the models that generated them has been done in education, I think, for 25 years for National Assessment of Educational Progress, which is an enormous survey that's been done for 50 years, I think.
What's the approach to imputation there?
Well, what you're doing is you're imputing what they call plausible values. You're multiply imputing values that might have been observed. And because educators, even not very sophisticated ones, often know about, quote, true score theory or something. Every test score is really, even no matter what to get a score, it's not your true score.
Right.
And so you generate a bunch of test scores you could have gotten.
Yeah.
And they understand that. Yeah, so these are possible values. And so the true score is the average of these things. Average of plausible values.
And that's generated.
I don't want to interrupt, but
Yeah, I'm
we're already
sorry.
running
Yeah,
a little over.
sure.
You
Okay,
guys
sure,
feel
sure.
free to
Yes.
continue, but